Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to start a new topic of discussion which is on impedance matching. For this video, firstly, I will explain what is actually impedance matching and what will be the role of impedance matching, why this is so important in order for us to achieve maximum power transfer. Next, I'm going to explain the two situations under impedance matching, under the match condition and also the mismatch condition. I'm going to explain what will happen, under these two scenario on the impedance matching. So basically, this will be the objective of this video. Guys, if you're keen to know more about impedance matching, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on impedance matching. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly understand the first three diagram on your left. So from the first diagram here, you can see that the impedance of the source and also the impedance of the load, they are the same. So under this criteria, we call this maximum power transfer, which means that all the power from the source are mainly delivered to the load, since their impedance are the same. However, when the impedance, you can see from here, they are different. The source and the load impedance, they are different. And because of this, we actually has this return loss. And once we have this return loss, we are not able to achieve maximum power transfer because some of them actually reflected back to the source. And hence, we are not longer maximum power transfer. You can see that from these two situations here, the first situation, because the impedance, they are the same and maximum power transfer actually occur. While on the second scenario here, you can see that because of the mismatch of impedance, so hence some of the power will be reflected back, and definitely there will be even more power that will be delivered to the load. The next diagram here, you can see that there are a further so-called mismatch impedance between the source and the load. And again, you can imagine that more will be reflected back and lesser will be propagated towards the load. So this is actually what is impedance matching. So which I will explain later on. Let's take a look on this animation here. So this is what I mentioned earlier on. Under perfect, which means that the impedance match, all the power from the source will be able to deliver to the load. Under this situation here, because there will be some form of mismatch, you can see from this diagram here, so this is from source, some will be able to propagate to the load, while you can see that actually some will be reflected back. So this is actually for the condition of mismatch. When the mismatch is further so-called highlight by the key difference between the impedance, as you can see from here, this is even so-called higher mismatch, more power will be reflected back, lesser power will be propagated towards the load. So basically, this is what impedance matching is all about. Because there are some amount of power reflected back, and hence we need to do impedance matching to reduce so-called as much as possible the reflected wave so as to achieve maximum power transfer from the source to the load. So this is what is actually impedance matching. Let me explain with this diagram. So this will be the source, this will be the load. So basically when I actually look into the ZS, the source, and also the ZL, so if let's say there will be some mismatch, then you can imagine that all the power that's sent from the transmitter towards the antenna we actually want all the power from the transmitter sent all the way to the antenna and basically radiate out. However, because there are some form of mismatch, some will be reflected back to the transmitter, and this is undesired because for this case here, as I mentioned, we want all the power from the transmitter reach the antenna and finally radiate out to the receiver. But for this case here, because there is so-called a key difference between impedance, and hence some will be reflected back. So what is the role of impedance? Let's say, okay, if we insert impedance matching in between the transmitter and also the load. Okay, so over here now, okay, when we actually look into the ZS and ZL, they are equal. So imagine when I actually put some device over here, okay, which means that ZS equals to ZL, then I will be able to achieve maximum power transfer. Because since the impedance they are the same, you can imagine that all the power will be able to pass it on to the impedance matching and finally to the antenna and finally radiate up to all the recipient. This is the objective of impedance matching. They actually sit in between the source and the load, and when we actually look inside here, okay, they are the same. Okay, but for some cases, okay, so these are so-called the real number, but in some cases which involve imaginary number, then ZS need to be complex conjugate with Z load. Okay, so basically beside the impedance, okay, must the impedance, which is the real number, they must be the same. But as I mentioned earlier on, let's say this is a complex number, so ZS need to be complex conjugate. Okay, ZL need to be complex conjugate of ZS in order to achieve maximum power transfer. Okay, please take note of this. Okay, so but in order to make this easier for us to understand, just concentrate on the real number for this so-called this discussion. We will leave the so-called complex number later on to understand this better. But over here, like I mentioned, I will keep it easier, okay, for us to start on the first discussion on impedance matching. Next, one is actually impedance matching, which I have described. Okay, but over here, I just want to quickly describe this again. Impedance matching, in fact, will be a technique in electrical engineering that aims to minimize signal reflection and maximum power transfer by making the impedance of a source match the impedance of a load, which I have explained earlier on. So the key idea is when we actually put the impedance matching, okay, so we want to match the two impedance, and because of this, we actually has maximum power transfer. Okay, this is very important in RF design where efficient power transfer is actually critical. Why is matching important? Without impedance matching, a signal encounter a mismatched impedance will be reflected back towards the source, reducing the power delivered to the load and potentially cause signal distortion, which can be explained by this diagram, which I have highlighted earlier on. Okay, so when we actually has so-called match, okay, lesser will be reflected back to the source. And because of this, we actually has maximum power transfer. Okay, so hopefully with this, you have a better idea what is actually impedance matching. Impedance matching can be achieved through various techniques. Okay, so over here you can see that there are actually four techniques. Transformer, resistive matching, reactance matching, and also matching network. The transformer actually can transform the impedance level, okay, that allow for match between a source and load with different impedance. As for resistive matching, okay, basically we use this resistor network so as to damp the impedance and hence to reduce the reflection. Next, on the reactance matching, okay, so reactance matching actually use capacitor or inductor, okay, to adjust the impedance at a specific frequency according to the electronics designs. Last but not least, on the matching network, okay, there are all circuits that are actually designed to transform an impedance as discussed by microwave and RF. Okay, but over here you will be able to find all this series discussion under the playlist, under the description. Okay, you will be able to find one of the way to do impedance matching. Okay, before I continue, guys, I urge you to help this channel by like this video. Okay, when more guys actually help to like this video, this video will have a better chances to reach up to a larger audience. So guys, help me press the like button now. Again, urge you, if you have learned something from this video, and if you have not joined this learning committee, help me, okay, by subscribing to this channel and turn on your notification bell. Once again, thank you so much for your strong support. Let's quickly understand the two scenario under the match and also the so-called mismatch condition here. So let's start with the match condition. Okay, so under the match condition, okay, I will explain later on ZL equals to Z0 and also equals to ZS. Then we have this match condition here. Let's take a look on this diagram over here. Okay, so from here you can see that this diagram actually break into three parts. This is where the source is, this is the transmission line, and this is actually the load. Okay, so basically you can link this to this diagram here. So this is the source, which is the transmitter. Typically, we will join the antenna through a coaxial cable, for example. So therefore, the coaxial cable actually behave like a transmission line. And then the antenna can be a load over here. Okay, so basically this is what I mentioned. Okay, we can correlate these two diagrams. Okay, as one, and basically the source as a transmitter, the transmission line, which is the coaxial cable that link the transmitter and the antenna, while the load will be the antenna. Okay, so let's understand again based on the condition of mesh. Okay, so the figure above actually show a transmission line, okay, with a characteristics impedance Z0. Okay, so basically this is the characteristics impedance of the transmission line, which is connected between a source impedance ZS and also a load impedance ZL. Okay, in order to have maximum power transfer, firstly, okay, we need to ensure that ZS must be equals to Z0. Okay, if you still remember, okay, let me quickly mention this. Okay, in order to have so-called minimum reflection here, okay, we need to ensure that these two impedances are matched. Okay, because imagine earlier on I did mention that these two impedances, okay, so in order to match, to have minimum reflection, okay, we need to ensure these two things is matched. I come to this here. At the low end, okay, which is low end is here, okay, we also need to ensure that they are actually matched in order to have this match condition. Okay, so this is what we call the low end. Okay, again, let me just describe this. Okay, imagine, okay, the signal actually propagate from the transmission line, reach the load. Okay, if they are matched, maximum power transfer occur because all the waveform will be sent over to the load. However, if let's say Z0 is not equals to ZL, there will be reflection. And once there will be reflection, we don't have maximum power transfer because there will be some loss through the reflection. And hence we cannot so-called declare maximum power transfer anymore. But the condition in order to have maximum power transfer, Z0 need to be equals to ZL. And with this, you can imagine that all the source will be continue propagate to the ZL. The same scenario at over here. Again, if ZS is equals to Z0, all the signal from the source will be able to transfer to the transmission line. And then finally, they actually reach the load. And again, if they are the same, all the signal will be sent over to the load. So this is what I want to discuss. In order to achieve match condition, ZL must be equals to Z0 and also must be equals to ZS. And with this condition, we call this maximum power transfer because all the power from the source will be able to deliver to the load. Okay, so basically this is the first condition under the match condition. Okay, so this is further explained on this here. So once we have this match condition, okay, will be something that when we actually shout over, okay, all the signal will be able to propagate. None will be reflected back. So this is actually under the match condition here. Maximum power transfer from the source to the load. Okay, all the energy from the line is absorbed by the load. There is no reflected signal, as I explained earlier on. Okay, so transmission line is actually non-resonant or flat under match condition. I will explain this on my next slide. There is no standing wave. Okay, so basically they are flat, which means that the voltage and current, they are actually all constant because the impedance is constant. And hence, we call this flat under the match condition. Okay, the impedance anywhere near the transmission line is actually equals to Z0. Okay, which means that any point on the transmission line we have the impedance of Z0 under the match condition. This is what I mean here. The impedance anywhere along the transmission line equals to Z0 if we have this match condition. Okay, let me continue this. So this is actually for a match lossless, which means that nothing will be lost, which means that resistor will be zero, G will be equal to zero. The voltage and current, they will be constant along the transmission line. Because the impedance is constant, okay, will be continuous to be Z0, okay, as the impedance, and hence the voltage and current will also remain constant, as you can see from this diagram here. Okay, the voltage and current, they will remain constant because this is actually a lossless transmission line. Okay, but most of the case, we actually fall into this so-called realistic transmission line. It won't be lossless, it will be lossy. Okay, so for a matched transmission line with some loss, okay, you can see that the voltage and current decay slightly. Okay, because of the loss, so we have some form of decay. Okay, so basically you can see from this scenario, okay, resistor is not really equal to zero, very small, but there will be still some loss. So basically, this is under the match condition. Let's take a look on the mismatch condition. So basically, under this mismatch condition, you can see that ZL, let's say, is not equal to Z0. And you can imagine there will be refracted wave, okay, which I'm going to explain shortly here. Signal can propagate in both directions in a transmission line. Okay, so basically this is a transmission line. Signal can propagate in both directions, which means that forward and also reflected, as I explained earlier on. The signal that actually propagate from the source towards the load, this is what we call the incident wave. And the signal propagate from the load towards the source. This is what we call the refracted wave. Okay, so over here, we understand that there will be two waves on the transmission line, the incident wave and also the refracted wave, as we mentioned over here. The incidence and refracted wave actually occur combined to form this standing wave. Okay, so if you are not so sure about voltage standing wave, okay, I suggest you take a look on my so-called other video on this voltage standing wave. But over here, let's quickly explain on this here. So this is actually the transmission line. Okay, you can see from here the Vmax will occur after 0.5 lambda. Okay, so this thing will repeat. Okay, so because this is periodic and this thing will be so-called repeat. So in short over here, when we actually has this so-called waveform actually propagate along the transmission line, but because there is a mismatch between the characteristics impedance of the transmission line and also the load, and therefore some signal will be reflected back. So with this, you can see that the impedance of the transmission line will not be constant Z0 anymore. And because there will be a so-called a change, values of the Z0, okay, and therefore we have actually a change on the voltage also. This is basically on the standing wave that we actually describe. Okay, so we don't talk so much on so-called voltage and current, okay, under this high frequency, but on the standing wave. So basically, this is actually the voltage standing wave. Okay, but like I mentioned, because this video, okay, I will emphasize more on impedance matching. Okay, I will leave this discussion maybe later on. Okay, but over here, okay, you can see that because of mismatch, we are going to have a refracted signal. And once we have this refracted signal, we don't have a constant voltage, constant current anymore. Okay, as you can see from this diagram here. Okay, the power generated by the source will be partially absorbed by the load. Okay, the rest is reflected to the source. No maximum power transfer. Extreme case of mismatch, okay, when they actually occur. Okay, for example, when ZL, okay, over here, okay, they can be open circuit or short circuit. So this is under the extreme case. Okay, so what happened here is basically when they are open circuit or short circuit, okay, so the total reflection actually occur at the load. No power is actually absorbed by the load. Okay, so from here you can see that under this case here, ZL can be either equals to infinity or ZL equals to zero. Okay, for short circuit it will be zero, open circuit, the ZL will be infinity. And because of this, okay, nothing will be absorbed by the load. Okay, so if you still remember, every 0.5 lambda will be a repeat of the scenario. So basically from here, imagine, let's say this is open circuit. After 0.5 lambda, this part here will be also open circuit. And this can be very so-called drastic, okay, when we actually do this impedance matching here. Okay, for a mismatched line, the impedance is actually different at different point of the line. The impedance actually repeat at every half wavelength, which I have mentioned earlier on. Okay, so basically this is actually under the mismatch condition here. And this video, I have also just quickly mentioned about the extreme case, okay, under the loop, which is open circuit and also short circuit. Okay, after this so-called half of the wavelength, okay, this thing actually repeat, and this can be quite drastic effect for impedance matching because this is so-called under the extreme case here. Okay, let's come to the disadvantage of mismatch. Okay, the presence of refracted wave actually in addition to the incident wave or apply signal where there is mismatch, maximum power transfer will not be able to obtain. Okay, so basically this is the biggest disadvantage. Okay, because not all the power actually sent to the load and there will be some reflected signal, and because of this, we don't have maximum power transfer anymore. The reflection of power from the load actually may damage the source. As I mentioned that we don't design so-called, let's say, for the protection, and because of the reflection of the power, okay, it may damage the source. The presence of high voltage standing wave may also cause cable dielectric breakdown. Okay, as you can see from here, if we don't have a design on the mesh condition, okay, so these two scenario may happen, and the so-called the device or the system may be damaged by these two so-called scenario here. Okay, with this, I hope you have a better understanding on impedance matching. Okay, so I think with this, that's all for today's discussion. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you so much.